Today I'll continue the discussion on the radiation pattern available from an edge-emitting semiconductor laser, and then I'll go on to a small problem discussing the longitudinal mode separation of a semiconductor laser, and finally I'll conclude by giving you an idea of what are the steps for device fabrication. So to continue where I left off last time, if you look at this diagram, this is the geometry of a stripe geometry edge emitting laser, and I'd drawn this last time. So the aperture, the actual aperture where the light comes from, is the intersection of the stripe width, which is S, this is S, and the other confining geometry is D, the width of the active region. And the light emerges in a cone, and since D is much less than S, we have the condition that the divergence in the X direction, that's the cone is theta perpendicular, is much larger than the divergence within the plane, which is theta parallel. This is a two-dimensional diagram of the same thing. This is a slab waveguide. This is the confining region of width D, and in this plane, okay, this is the plane, and this is the divergence. Okay, if this is vertical, then this angle is theta perpendicular. Now, how does one actually derive what are the values of theta parallel and perpendicular? Well, it's done by, again, using the wave equation and looking at the intensity coming out. We know from the wave equation that d2 Ey dx squared plus d2 Ey delta z squared, and in free space we have mu 0 into epsilon 0, okay, whereas within the medium this was epsilon semiconductor, Ey over delta t squared. Now again we take recourse to separation of variables. We say that let Ey x z t is equal to some function which is a function of only x, z, and t, and we have the condition that boundary condition that the intensities must be continuous at z is equal to 0 at the boundary between the semiconductor and the air interface. Use separation of variables, and then we come out with a relation of this type. E y x z is E u exponential minus j u k 0 x into exponential minus j into 1 minus u squared to the power half k0z. This is propagating in the z direction. So from this we find E theta, and as I mentioned last time, the radiation pattern is just I theta over I 0 at theta equal to 0 is equal to E theta over E0 squared, and this, from what I've shown before, goes as cos squared theta perpendicular minus infinity to plus infinity Ey x 0, that's z, into exponential j sine theta perpendicular K0x dx. This whole thing is the magnitude squared over Py x0 dx magnitude squared. So we have this cos squared variation, and where theta perpendicular is the width of the pattern between the half power points. So if we plot this, then we get the radiation profile that I've shown here, where typically we have theta parallel is of the order of 10 degrees and theta perpendicular is of the order of 35 to 65 degrees. So this divergence is much more than in a gas laser or in a solid state laser, mainly because the emitting geometry is extremely small, and there is diffraction from this small aperture, and the smaller the dimension, the larger is the divergence. Obviously, if you want to use a semiconductor laser for applications where you want a low divergence beam, obviously we have to have the suitable optics which will focus this, which will narrow this divergence and give a very pointed low divergence beam. Coming to the next point, so this immediately shows the semiconductor laser has characteristics rather different from a gas laser or a solid state laser. Another point of difference is regarding the modal pattern. In a semiconductor laser, if we measure the output when it's lasing, we find so we have a number of modes. This is the intensity in a typical Fabry-Perot type of cavity, where we have a laser cavity length L. Okay, this is the gain medium. We have mirrors, and we've seen that when the path length twice n bar L is equal to m lambda, we can have a number of modes corresponding to different values of m. Okay, so we want only one particular mode to operate, and we want to find out what this modal separation is, delta lambda. Okay, so let's work out a problem where we have a gallium arsenide laser working at 0.89 micron. N bar is 3.58 refractive index of the active region. L, length of the cavity, is 300 microns. And we know from the relation that I gave you that we can find the modal separation by differentiating and simplifying. We get delta lambda is lambda squared delta m over twice n bar L into 1 minus lambda by n bar into dn bar d lambda. Okay, this is a dispersion term which arises due to the fact that the refractive index of the medium varies with wavelength. Okay, this is not equal to 0. So there is a certain variation of refractive index with wavelength. So if we use this expression and we take delta m is equal to 1, we want the separation between individual modes, we substitute in that. We find delta m lambda is lambda squared, okay, 0.89 to 10 to the power minus 4 micron squared over twice 3.58. You have to get the units right. We're working in centimeters, so 300 microns, okay, into 1 minus 0.89 by 3.58, and that is 2.58 in micron inverse. Okay. So if we just work this out, it comes delta lambda comes out to be 9.74 angstroms. Okay, which is so this separation is of the order of about 10 angstroms, which is not too small, neither is it too large. Now, if you want to increase the mode separation, then what do you want to do? If you look at this expression, okay, obviously for longer wavelengths you'll have higher mode separation. There's nothing much you can do about n bar, but if you have smaller L, then you'll get a larger mode separation. Okay, and these are sort of material constants, etc. So this is again. Pardon? Yeah, if you want to select only one particular mode, you would like to have a larger separation. Of course, there are other ways. This is just looking at the cavity dimension, but there are other ways. If, for example, we find that in this diagram, if we plot which mode will operate, the one that will have gain. Okay, suppose the gain versus loss curve is something like, suppose the overall loss is something like this alpha, and the gain curve is something like this gain curve. Okay, I'll discuss this later for particular structures. So if the gain curve is rather flat, okay, then all the modes will oscillate. But if you can tailor the gain to be like this, then only oscillations will be possible in this wavelength region. So this is mode selection through tailoring the gain. Okay, this can be done, as I'll show later, by having, instead of a Fabry-Perot cavity, if we have a cavity in which we have a diffraction grating. Okay, it's like a Bragg reflector, which is giving you distributed feedback. Okay, so in this case, only a particular wavelength which satisfies Bragg's law will have high gain. Okay, so this is one way of stabilizing the cavity to oscillate at one particular frequency. Okay, there are many ways. Using quantum well structures are other ways. Right. Next topic is, let us see about I have not talked about the temperature dependence of the threshold current. It turns out that the threshold current JTH is given by J0 exponential T by T0, where T0 is some constant. So the threshold current increases with increase in temperature. Okay, it will increase like that with increase in temperature, and we do not want this. This is undesirable. So how can you reduce the temperature dependence? If you have a high value of T0. Okay, So it turns out for gas-Al-gas lasers, T0 is of the order of about 150. This is just an empirical parameter. Okay, it's just an empirical parameter. Dimensions is degrees K. It's about 150 for gas-Al-gas lasers, but it's only of the order of 60 for indium gallium arsenide phosphide lasers. Okay. So these lasers have much stronger temperature dependence. These are typical double heterostructure. Okay. One of the advantages of quantum well lasers, etc., is that for the same system working at 1.3, 1.5 microns, this value of T0 is of the order of about 80 to 90 for multi-quantum well lasers. So that is another advantage of having quantum well structures rather than common double heterojunction structures. This is JTH, this is T. One can inquire as to why there is temperature dependence of threshold current. Well, obviously you will see that one of the reasons is the band gap, and hence the intrinsic carrier concentration. If you have low Eg, okay, you obviously at higher temperature you have higher Ni, and comparing these two, gas-Al-gas, here Eg is of the order of obviously about 1.4 eV, okay, and here Eg is of the order of 0.8 to 0.9 EV. So a material with lower band gap will obviously have a larger temperature dependence of the carrier concentration. Okay, so one of the reasons is the band gap. The other is leakage over barriers. Okay. This is looking at temperature dependence. Even if you have a double heterostructure or quantum well, obviously if you have a barrier like that, okay, this delta EC and delta EV is confining the carriers, but remember delta EC, delta EV are not very large. This is 0.2. Say for gallium arsenide this is larger, this is 0.4 EV, and this is of the order of about 0.2 EV. Okay, and KT is 25 milli-electron volts. So with higher temperature there is always some possibility or probability of carrier leakage outside the barrier. Okay, so this leakage current will reduce the radiative recombination. Instead of the carriers, electrons and holes recombining directly, okay, giving out light, confinement will be poorer, and so the threshold current will increase. In fact, you know, the expression for JTH, there will be, in practice, there will be a J leakage plus the J, radiative recombination. So this will increase. Another reason is that non-radiative recombination. Okay, Auger is highly temperature dependent. Okay, so Auger recombination increases with temperature. And remember, Auger recombination, it increases with temperature, and it is more for low band gap materials, right? There's a Eg to the power n relation. So the lower the band gap, more the Auger recombination. So one of the objectives of semiconductor laser design is not only to reduce the threshold current, but also to reduce the temperature dependence of the threshold current. And it can be done through choice of material, choice of geometry, choice of the quantum confinement effects, through many different techniques. Okay, so since we are talking about device properties, let me just mention some of the important parameters for a laser. We have already discussed some of these. One is, of course, threshold current and dJTH dt. Then the confinement factor gamma. For each structure we have to find out the confinement factor, because this determines JTH and dJTH. Okay. In actual application, the beam divergence is something important. Okay, we want to have structures with low beam divergence. Okay, we want to have single mode of operation. Okay, spectrum is important, and we obviously want to have a single mode operation. The line width is important. We want to have as low a line width as possible. Typically, the lowest line width that has been obtained is about 100 kilohertz with an externally stabilized cavity. 100 kilohertz is about the lowest. But typically, it's of the order of 1 to say 5 megahertz, which is low considering that this is delta F. F is of the order of 10 to the power 14 hertz. Okay, so it's relatively delta F by F is quite small. So we've discussed all of these in some depth, and there is another parameter that we have not discussed. I will discuss later, and that is the relaxation frequency of oscillations. This comes in when we are talking about the frequency response. What is the highest frequency at which the lasers can be modulated, etc. So this is it characterizes the coupling between the photon densities and the carriers. Okay, so these are the major parameters. So let's finish today's discussion by talking about device fabrication. Most of these devices are fabricated by rather similar techniques, even if we go for quantum well structures, etc. I'm not let's look at this view graph. I hope you can see this. Okay. Firstly, if we look at the material aspect, okay, for fiber optic communication, we want to operate at wave 1.3, 1.5 wavelengths. This is the usual band gap versus lattice constant. So if we want lattice matched devices, then we have to stick to this straight line. If we want lattice mismatched devices, we can grow in gas on gallium arsenide, etc. So that is a major new development. That is strain layer, which I will come to gradually. So the first step in device fabrication is obviously growth of epitaxial layers of, say, gallium indium arsenide phosphide with the right composition. It can be double heterojunction structure or quantum well structure or strain layer structure. Once these layers are grown, then we follow this device processing cycle. maybe I will draw them and show them later. This is the first stage. Okay, maybe we have a substrate. Okay, substrate is quite thick. It's of the order of 350 microns or 400 microns, depending upon the wafer size. If the wafer size is 2-inch, substrate thickness is 350 microns. Okay, if this is N plus, say, indium phosphide, then what do we grow? We grow, and by MOCVD, we grow first a buffer layer. Same material, indium phosphide. Then we grow, okay, there'll be a different indium gallium arsenide phosphide. Okay, X1 minus X. Then we, with probably a low value, indium phosphide has a band gap of about 1.4. We grow a material with a band gap of, say, about 1.1 eV. Okay. Then we grow another layer with a slightly different value, indium gallium arsenide phosphide, with a band gap of, say, 0.9 eV. Okay. Then we grow the active layer, D, typically, say a double heterostructure, D 0.2 microns. All this is N. Okay. Active layer is undoped, and then on the top we grow an indium gallium arsenide phosphide, P-type dopant, typically zinc, P. Then we have a P plus, and the top layer could be a P plus indium gallium arsenide, which is low band gap, which will give you ohmic contacts. Okay, so although this dimension is rather exaggerated, this is 350 microns, but the entire this top dimension, would be of the order of a few microns. Okay, this whole thing is of the order of a few microns at the most. Okay, now we are talking about say a stripe geometry, which is a practical device. Suppose you just want to test this device. Okay, then what can you do? You just evaporate ohmic contact. Okay, you want to, on N plus indium phosphide, ohmic contact would be typical gold germanium alloy. Okay, on P plus, P type, it will be gold zinc. Or you can have multi-layer. I'm describing the simplest. This is an alloy. Okay, zinc is a P-type impurity, so it diffuses and gives you a low resistance contact here. Of course, there are other ways you can have multi-layer. You can deposit titanium, palladium, gold, zinc, etc. But I'm sticking to the simplest. Okay. Now, so if you evaporate over the whole area immediately and cleave and make a device, you will get a broad area. But if you want to make a stripe geometry device, then you go back to the flow sheet. We want to define this stripe. Okay, so what do we do? On this substrate with the grown layers, okay, we grow. Let's see if silicon nitride, typical by plasma CVD. Okay, so that the temperature of growth is reasonably low, something like 250 degrees centigrade. Why? Because you do not want the device structure to be exposed to high temperatures. You will get interdiffusion. You do want to avoid interdiffusion. Okay, this may be thickness of the order of about 1,000 angstroms or so. Then, with appropriate masks, okay, then you deposit a photoresist Okay. Then you have the mask coming on top. Okay. With the defining geometry. This is the stripe width S, which is of the order of, say, 5 to 30 microns. So that is this step. You on silicon nitride photoresist, you expose the photoresist and etch the stripe, and as a result you will get silicon nitride remaining in this portion, silicon nitride remaining, and no silicon nitride below this. Okay. Remember, this is the top p-type side. Then we deposit zinc gold zinc alloy, metal right over this, and sometimes to get good conductivity, low conductivity, you plate. Okay, you electroplate a thicker layer. So let's look at the top of the device. Here we have silicon nitride. Okay, silicon nitride, and at the beginning you deposit a thin layer. Okay, by evaporation, gold zinc. Evaporation gives you only a few thousand angstroms. You may then plate, use that as an electroplate. Okay, and in a zinc bath and get something of the order of a few microns thick. Okay. Now we started off with, okay, if we draw it to the right geometry, okay, the layers are over here, okay, and this is the substrate, which is 350 microns. To form the cavity, we have to cleave. Okay, so cleavage is done much more easily and more uniformly if we can thin the substrate. Okay, so by lapping, so this is an important step. We lap the substrate down to about 100 microns. This can be done over the whole wafer, okay, the whole piece. So this is removed. Okay. And remember, this is the inactive side. This is just the back of the wafer, but it has to be done uniformly. It has to be done, you cannot do it at an angle, so it has to be done pretty carefully. So you thin to 100 microns. Okay. Then what do? We are left with a material which is thinned with the gold zinc layer. We want to make ohmic contacts to this. Of course, one of the other advantages of thinning, okay, what are the advantages of thinning? Firstly, easy cleavage. Okay. Okay. What are the cleavage directions in these materials, indium phosphide, gallium arsenide? What are the cleavage planes? Yeah, okay. So indium phosphide also. So cleavage planes are 110. Okay. So if you put pressure, it will cleave along 110 because these are non-polar. Okay. One of the other advantages of cleaving is easy cleavage is 1, and of course it lowers the bulk, lowers series resistance. Okay. because after all, this is an inactive region. It's 100 microns thick. The rest of it is only a few microns thick. Okay, so it lowers the series resistance also, and this is important in lasers. And on this side now, you can plate. There are different materials for ohmic contacts. One of the materials that you can use are typically tin, nickel, gold. Okay, gold provides the high conductivity. Tin is an N-type dopant. Okay, and nickel is helpful in forming the right alloy. Okay, so you evaporate this as the ohmic contact. Okay. Then, well, I can look at this diagram. On top of this, in order to get better contacts, what you could do is, you can do a multi-layer contact. You can titanium, as a sort of a diffusion barrier, and then you can evaporate or gold overall. Gold. Why do you have to take a lot of care on this p-type side? The reason is, of course, that this geometry, this area being very limited, the series resistance builds up. Is much more here than here. And of course, ohmic contacts to p-type materials are intrinsically more difficult than ohmic contacts to n-type materials. So you have to take all the trouble of making very low series resistance contacts to this. If I go back to this diagram, we are here. We can evaporate a gold pad on that. Then we can put the material on a rubber pad, and we can scribe in the lasers. If the material is like that, we can manually scribe these, and they break up into small slivers, and then if we exert pressure on these, they will cleave, into small devices which are typically of the order of length is about 300 microns, and the thickness is already of the order of 150 microns, and the stripe width is of the order of a few microns. So we cleave here, and we saw the make the device. These are the bonding pads, on the stripe. Remember, the rest of there's silicon nitride, which is preventing current flowing right through the device. So this is a stripe geometry, and here comes an interesting step. What is then done is that we invert the device. This p-type side is bonded down on a gold-plated copper heatsink. Why? Because it makes for easier bonding. And also because this is a small area, whereas this is a large area, and the gold wire is bonded to the substrate side. Another advantage of this is, where is the junction? The junction is right here at the top somewhere. So the junction is much closer to the heatsink. So this is a standard geometry edge emitting device, and the light will come out from the edge of the wafer. I have a small device here, which I don't know if you can see. This is you can see most of it is a massive heat sink. This, incidentally, is a device that was made in 1977. Okay, RCA, double heterojunction. The threshold current of this is 75 amperes. So as a result, this device has never been used. The power supply required for this is 200 nanosecond and 75 amperes threshold current. It will give you, some 20 or 30 watts output. And you find right at the edge, there's a little tiny device, okay, mounted on the edge. You can come up later and see it. Okay, and the rest of it is all a heat sink. This has to be screwed in very tightly. There's one lead. This is ground, and this is the other active lead. Okay, and this device is mounted on a sort of a ledge, okay, on a cut ledge, and the light comes out like that. Okay, so this is a conventional double heterostructure laser with threshold current. J is of the order of a few thousand amps per centimeter squared. The operating current is 75 amps. Okay, this is 77 device, and if you compare it with this is a 97 device. Okay, so this is a semiconductor laser. Threshold current 20 or 30 milliamps. Here the threshold current, okay, this is 75 amps. Okay, and this is even less than 75 milliamps. So in 20 years, the threshold current has gone down by a factor of 1,000. And most of this is just the battery. This is a visible light emitting device. The output power, it says, is about about a few milliwatts. Okay, so it's reasonable, of course. And of course, this is watts of power. Okay, so that's the basic difference. But this can only be worked under pulsed operation. 200 nanos, because the duty cycle has to be very low, because the overall power depends upon the current into voltage into duty cycle. Okay, and the duty cycle here should be about 1 by 1,000 or something like that. Okay, 1 by 10,000.
Please on the laser.
Which one?
That laser.
Can you see it?
This. This.
Okay. I hope it doesn't. Okay. Okay, fine. So in the next talk, we'll go on to more advanced types of lasers, strain layer, quantum well lasers, etc. But before that, I think I'll have to discuss a little bit about the optical spectrum coming out from a laser. And here I will go back and talk about the gain mechanisms. I'll talk about the Van Roosbrecht-Shockley condition, which relates the radiative recombination with absorption.